Hey everyone. So I'm sorry about the poor lighting and poor angle, but that's what we got going for us. So now we're going to solve the two-dimensional problem. So here in this situation we have two pucks of equal mass, both 100 grams, which is 0.1 kilograms, and they collide on an air hockey table. And we neglect friction. That's good. It's important we neglect friction because we want an isolated system if we're going to use momentum conservation. So this basically tells us our system was isolated, so we can use momentum conservation. So prior to the collision, our first puck is traveling in a direction we're going to call our positive x-axis at 1 meters per second. All right, so initially we have a puck here, label it as puck 1, traveling to the right at 1 meter per second. And then we also have puck 2 traveling in the y direction, in the negative y direction at 2 meters per second prior to the collision. So we've got another puck 2 here, moving downwards at 2 meters per second. Just note, were you able to see any of that? I don't even know. So just note that my vectors here, they're more arrows. They're not necessarily vectors because they're not drawn to scale, right? This vector should actually be longer than this vector here. But here we're moving at negative 2 meters per second, and puck 1 is moving at 1 meters per second. All right, they collide. So let's say they collide here. And after the collision, puck 2 travels at 30 degrees above the positive x direction. All right, so after the collision, so I'm just going to draw a dotted line here to represent my horizontal axis, my x-axis. So this is saying that puck 2, once they collide, so let's say here's where they collided. Is that the word collided? I guess so. Puck 2 is going to move off this way at an angle here of theta, which is equal to 30 degrees. Okay. And we're also told that it moves off at a speed of 0.8 meters per second. We want to find the velocity. So since velocity is a vector, that's both magnitude and direction, of puck 1 after the collision. So we don't know what direction or with what magnitude puck 1 goes when they collide. Just based on intuition, right? If we've got something moving to the right and something moving down, and then something moves off in this direction, we probably should suspect that puck 1 is going to go off at some negative angle, some this way. So even though I'm not going to draw it, we know puck 1's going to go somewhere, we don't know where, but I suspect it's going to be something off like this. All right, so let's see if that intuition is correct. So puck 1, we don't know what's going on. So here's we're going to implement two-dimensional momentum conservation. So that is to say that our initial total momentum in the x direction is going to be equal to our final total momentum in the x direction. And same thing for the y. So initial total momentum in our y direction is going to be equal to our final total momentum in the y direction. So essentially here in my drawings, I've actually drawn the situation before our collision, so initial, and after our collision, so our final situation. So if we wanted to find, so let's look at our initial. So we're looking at the left-hand side of our equation here. If we want to find the initial total momentum in the x direction, so we have two objects here, so we can have up to two terms. So object 1 is moving along our x direction, so we're calling, I was sloppy and didn't label my coordinate system, positive x to the right, positive y up. All right, so we said puck 1 is moving to the right, so it does have a momentum. Both the objects have the same mass. I'm just going to call that mass m. So we have the mass of puck 1, m, times the initial velocity of puck 1 in the x direction. All right, so I'm going to have a lot of subscripts going on, but I'll try to keep them in the same order. So we have initial velocity of puck 1 in the x direction. Puck 2, it's initially moving in the y direction, has no x direction motion at all. So that's, we only have to worry about here. Initial total momentum in the y direction is going to be the mass of puck 2, which is just m, times the initial velocity of puck 2 in the y direction. All right, so just to be consistent with my variables so I can look at them for later reference, I called my 1 meters per second to be initial velocity of 1 in the x. Negative 2 meters per second was initial velocity of 2 in the y. So we have found expressions for both this and this. So now we need to worry about the right-hand sides of our equations here. So what's going to be helpful is we know what the final momentum of puck 2 is. Right? We know it has a magnitude of 8.8 meters per second, or that's its velocity. We multiply that by the mass of puck 2 at an angle of 30 degrees. And I'm calling that angle theta. That's a theta there. Sorry, it's kind of tough to see. All right, so let's redraw this in terms of the x and y components, right? So we know this vector here goes off at an angle, and we're dealing with x and y components. So we want to use some trig to break that up. So we'll call this velocity final of puck 2, because we know that's going to be the final velocity of puck 2 is going to be this 0.8 meters per second. So I'll also label that up here. Velocity final of 2. So we know that's going to be equal. So you can break it up to, that velocity is going to be equal to these component vectors added together. So we have a vector here pointing to the right along our x direction. So we'll call that our final velocity of block 2 in the x. And we also have velocity final of puck 2 in the y. And this angle here is our angle theta of 30 degrees. So if we were to find the momentum of, so now we have enough information to find the final momentum expressions. So let's first look at our final momentum total in the x direction. Here, if we look at our x component, we know we have a velocity for puck 2 to the right here. But we don't know about puck 1, so we have to write an expression for puck 1 to see if it has one. It probably will. It probably will have an x component. And if it doesn't, the math will tell us, but if it does, it will. So we have the mass of puck 1, so just m, times the final velocity of puck 1 in the x direction, plus the mass of puck 2 times the final velocity of puck 2 in the x direction. If we're dealing with the x and y direction, so here, if I were to rewrite, so looking at for puck 2, the final velocity of puck 2 in the x, if we're dealing with, let's look at our angle theta. Theta here is, actually looks like cosine. Cosine of theta is adjacent over hypotenuse. So that's final velocity of puck 2 in the x divided by our hypotenuse. It's velocity, it's final velocity for puck 2. So then we see that our final velocity of puck 2 in the x is going to be equal to, I'm really sorry about the lighting, you guys. This was what happens when it gets dark at like 4:30. So it's going to be our final velocity of puck 2 times the cosine of theta. Similarly, for the y direction, I'm just going to write this now. We'll have final velocity of puck 2 in the y is VF2 sine theta. Very similar to when we dealt with forces. All right, coming back here. If we did a similar thing, we'll see that the x component, if we're dealing with puck 1, is also going to be a cosine. So we have the mass times the final velocity of puck 1 times the cosine of, we don't know that angle yet, right? We don't know the angle of which that velocity vector for puck 1 is going to be. So I'm going to call that phi, right? Phi is usually a symbol we use for another angle in addition to theta. And we know that, and we have here, so that's for puck 1, and puck 2 is mass times the final velocity of puck 2 times the cosine of that 30 degrees, so what we call theta. And similarly, we can write an expression for our total momentum in the y direction, the final total momentum in the y. So it's going to be mass. So look, we do the momentum of puck 1 in the y direction. So it's m, our final velocity of 1 in the y, plus mass final velocity of 2 in the y. All right, so puck 1, puck 2, momentum of puck 1 in the y, momentum of puck 2 in the y. Breaking it down to components, the y components are going to be sines. So we have mass times our final velocity of puck 1 times the cosine of this angle we don't know yet, plus mass final velocity of puck 2 times, oh, not cosine. Man, this is going to be a sine. All right, and here's also a sine of theta. Writing both these equations together, we have, all right, so now we're applying momentum conservation. So we're going back up here and plugging in our variables. So we have mass, so where am I? I've already lost what I'm going on here. So initial total momentum in the x component is mass times initial velocity of 1 in the x, and that's going to be equal to our final momentum in the x, which was this expression here. M VF1 cosine of phi plus M VF2 times the cosine of theta. And then we have our y direction. So in the y direction, our initial momentum, we said was just mass times the initial velocity of 2 in the y. And that's going to be equal to this expression we found here, which was mass times our final velocity of object 1 times the sine of phi plus mass final velocity object 2 times the sine of theta. So if you look at these expressions, what's really nice is mass cancels out in every single term. All right, so mass cancels out. So now we have two equations, and hopefully we only have two unknowns, right? So initial velocity in the x, we do know. That's 1 meters per second. Final velocity 1, we don't know. That's actually something we're solving for. We're solving for this. Phi, we do not know. That is also what we're solving for. VF2, we know. That is 0.8 meters per second. And theta, we know that's 30 degrees. Looking here, velocity of object 2, initially we know that's negative 2 meters per second. Do not forget the negative sign, that's very important. And then everything else here we know except for our two unknowns of our final velocity object 1. We're calculating the speed there. We have to be specific. And then our angle of phi. So we have two equations and two unknowns, so we have enough to solve. So you can look at my next video if you want to see how to solve this explicitly.